Is that sufficient?
Makes sense.
DJ?
So is that why, like, when you rub something together, it becomes hotter? It's just because of the. Okay.
And there's an example where a thermodynamics demo / lab where you take a container with something that easily moves back and forth, generally iron metal filings. You find the temperature of it, and then you move it back and forth like this so that all the metal filings are moving down, back and forth, and then you take the temperature again. And based upon how far they moved, you can come up with an estimate for what the final temperature would be.
So would that mean that you were talking about hitting the ball, whatever? Does that mean like the harder you hit the ball, the hotter that the ball's gonna be? Or the warmer?
I think you could easily make that argument, because it can only, yeah,
I mean, there's like that.
there's always gonna be a loss somewhere in reality. The question is, when can you assume there is no loss?
There's like that. I've heard this argument. It's very, to me, it's like really stupid. But I've heard it before. Like how hard if you had a chicken and like you wanted to slap that chicken and like cook it immediately, how hard would you need to slap the chicken to cook it immediately?
Alright.
If you're familiar with what if, if you take a frozen steak and you drop it, from how high up do you need to drop a steak in order for it to be cooked by the time it hits the ground?
That's awesome.
And he came to the conclusion that what would happen is that the outer part would cook,
Yeah.
and eventually part of that would turn to ash, and so you'd lose this. When it eventually hits the ground, it's smaller, but ultimately you'd have the outside cooked, but the inside would still be frozen. But it
Yeah, so
really,
it'd
I guess,
just be
depends on
rare.
the size steak. Pardon?
It'd just be rare, right?
Yeah, or steak tartare, there we go. If you're not familiar with What If, it's a website, podcast, I'm not quite sure what it is right now, there's a book as well. There used to be a post in Allman on the 3rd floor about relativistic baseball. If you could throw a baseball near the speed of light, what would happen?
Burn out.
Not only that, but it would cause fusion reactions, and the entire ball field, and probably the city would explode.
The white covered bush? The white covered bush, I think I have that.
It's possible,
And it would always be like, when I was like younger, I'd just read it, and it was like very random, and it did a lot of stuff with like space and like speed of light stuff, so I think that might be it.
And serious answers to silly questions, I think, is the
Yeah.
underlying slogan. All right, I want to do one more thing, then we're going to take a break. What is the change in momentum of the 2 kilogram mass? Well, we know P initial.
0.
No. The change in momentum of the entire system is 0, but not for the 2 kilogram mass. So what is P final for the 2? I know the mass.
Is it the, sorry, the 7, or yeah.
Wouldn't it just be 2?
Why just 2?
Because it's only moving at 1 meter per second and its mass is 2 kilograms.
All right. Oh, while we're here, what is the 5? What's the final momentum of the 5 kilogram mass?
It'd just be 5.
5D.
So, if I want to look at the change in momentum of the 2 kilogram mass, what is the change?
60.
14?
Oh no, never mind. How would it be 4? What was it? 4 times 2 would be 6.
That's what I thought, I'm just looking for the difference in the.
Yeah, you are looking for the difference.
Wait, so initial was.
What's the initial?
Is it P final minus P initial, is that where we're going on?
It is P final minus P initial. Yep. Therefore,
10
It's
big,
10.
2 minus -8.
yeah, I was doing that.
What about for P5 final?
10?
No.
No?
Oh,
Negative.
sorry, change in momentum,
Negative 10.
Negative 10.
negative 10. So the amount of change in momentum here and the amount of change in momentum there should add up to 0 in a closed system. So that one's 10, the other's negative 10, that makes sense, feels right. This part of this gets into semantics here. The momentum of the 5 kilogram mass changed by negative 10 Descartes. So the 2 kilogram mass exerted negative 10 Descartes of impulse on the 5 kilogram mass. The 5 kilogram mass exerted 10 Descartes of impulse on the 2 kilogram mass. So in an open system where I'm only looking at just this object, my momentum did change. In the closed system where I took both of them into account, my total momentum did not change. All right. Any questions? All right, let's take a break. I'm going to pause this and pretend I will remember to turn it back on.
Slap a piece of chicken and would cook it.
Water or,
eventually.
yeah, whatever components are in it, but it's so
The trouble is that you're applying kinetic energy into it, transferring energy, trying to get the molecules heated up. At some point, if they're vibrating so fast, when you slap it with your hand, if I was just slapping it with my hand normally, then it's possible that some of the energy would be transferred back to my hand and I would no longer be heating it up. But I have not tried it, so if one of you wants to try it and then videotape it, or video it,
Okay.
videotape a little archaic, but
To answer
sure.
your question now, one average slap will generate a temperature increase of 0.0089 degrees Celsius. It would take 23,034 average slaps to cook a chicken.
But then you have to
Account.
think
Yeah.
that it cools.
Yeah.
You've,
Kinda like-
you've seen that video of the guy, he has a machine that's punching meat and he
Yeah.
cooks it, yeah.
Yeah.
So if you do it enough.
I didn't know that existed.
But you have to mention it as long as it's in
It's a good video.
All right. Let's bring this back into the perfectly elastic collision. So this will be the other part of the test. I will ask, typically this is the first question, and part B is the perfectly elastic collision. Now, part of it, I am assuming that the masses stay the same as they were before. So I have two equations here. I have 5 times 3 plus 4 times negative 2 is equal to 5 times V final, V5 final, plus 2V2 final. Bless you. This is my conservation of momentum. This is mass times velocity. This is P5 initial plus P5 final. Oops, try that one again. P2 initial is equal to P5 final plus P2 final. So the first equation, so I know momentum is conserved, collision, immediately think conservation of momentum. And now we have the other aspect of perfectly elastic collision, which tells me in perfectly elastic collision, the kinetic energy is conserved. So our second equation, K5 initial plus K2 initial is equal to K5 final plus K2 final. Now, this whole idea of kinetic energy being conserved, you might ask, is this even realistic?
No.
Depends. If I have two cars crashing into each other, kinetic energy is not gonna be conserved. If nothing else, you hear the crash, things will heat up, there's gonna be rubber left on the road, there's a lot of things going on there. In elementary particle physics, such as on my dissertation, we're dealing with particles that you take protons that up near the speed of light, crash it into something else, you get a shower of particles coming out that have all sorts of, they'll collide and separate and so forth. At that level, friction does not exist. Nothing really like heat transfer, it's not called heat transfer at that point, it's just called energy transfer. Kinetic energy is being transferred from one object to another. So it is legitimate at that point to say kinetic energy is conserved. But we also have an unrealistic problem here, the fact that my system is just these two objects. There's no planet pulling it down, there's just two objects out in the middle of, in this universe that I've created. So, we've had it up here before, probably, it's not written up there right now, but in unison, you're gonna make me cry on the inside with joy. What's the formula for kinetic energy?
1/2 mv squared.
Initial squared plus 1/2 into V2 initial. Supposed to be a dot right there. Squared is equal to 1/2 M5 V5 final squared plus 1/2 into V final squared. I have my two equations here. If I plug in numbers, I get 1/2 times 5 times 2 squared plus 1/2 times 2 times 4 squared is equal to 1/2 times 5 times V5F squared plus 1/2 times 2 V2F squared. This on the left-hand side we've already done, it's 38.5. Questions how we have the two equations here. I have two equations, two unknowns. It becomes a math problem now. Any questions right now? All right, let's solve. So I have 7 is equal to 5. Now, a couple notes here. The more I write, the more chance I have to making an error. So this V5F, I'm just gonna use the letter C to represent that, and V2F, I'm gonna have that represented by the letter D. That is not D as in Descartes, but it's D as in I just want another letter. So that would be 7 is equal to 5C plus 2D. And then for my kinetic energy equation, 38.5 is equal to 2.5 C squared plus 1 D squared. Two equations, two unknowns.
I mean, in the top one, C would have to be 1 and 2 would have to be, D would have to be 1 because 5 plus 2 is 7.
Well, we'll find out if that's right. We have a prediction.
No, never mind. You could,
Well, no,
for the top equation, I either isolate C or D and then plug it in, but I feel like you're gonna show us a shortcut.
Not yet.
No.
Which one would you solve for?
Can't we set the equations equal to each other?
No, these are squared and those aren't.
Oh.
Which, D? I heard D as a dog. Alright, so solving for D, we get D is equal to 3.5 minus 2.5C. Subtract 5C from both sides and divide everything by 2. I can now plug that into the second equation. 38.5 is equal to 2.5C squared plus 3.5 minus 2.5C squared. $38.5 is equal to 2.5C squared plus, why did I pick these numbers? All right. 3.5 squared,
It's like, 3.5 squared is 12.25.
$12.25.
Yeah.
Alright, then twice, so 5 times 3.5, so that's 17.5. C plus 6.25 C squared. Okay, don't comfortable with this.
So now you just add. This just become a quadratic formula.
It is a quadratic equation, I can't really see it from there, so I've got 38.5 equals, so I've got 2.5C squared, that's 6.25C squared, so 8.75. Please?
Yes.
Now, when I get to the end, I will know if I've made a mistake or not, so it'd be nice to not make the mistake to begin with, though. And then 12.25. Bringing that over, we have 0 because it's a quadratic. Set it equal to 0 so we can use the formula. So I have 8.75 C squared minus 17.5 C minus,
Negative 26.25.
thank you. 17.5 plus or minus the square root of 17.5 squared minus 4 times 8.75 times negative 26.25 divided by 2 times 8.75.
Yeah, 3.
3 exactly?
Yeah.
Okay. Or,
Oh,
Or,
give me a sec.
or 229.6875, I believe. I might have calculated incorrectly.
yeah, something's wrong there.
Negative 1.
Not expecting that. Anyone else get negative 1?
Yeah, yeah.
Yeah.
3 negative 1.
Yeah, it's very, work out very nicely.
Oh, it's nice when it works out like that. That is, C was the speed, or velocity, sorry, it's the velocity of the 5 kilogram mass after the collision. One of these is correct and one of these is not.
Do we just plug them in and figure it out?
Can we look at it visually? Yes, in terms of which mass it's related to?
That's related to the 5 kilogram mass.
So it should be the negative 1 meter per second?
Why is it not the other one?
Because it was already going in when we defined right as positive, it was going in the positive direction, and then it got hit, and it started going the other way.
Wrong reason.
Okay.
Well, I remember there being like there is a 1 somewhere.
That one was, that we had before was for the perfectly inelastic
Does
collision.
that not matter here?
No, that doesn't, not this technique.
What's the question?
I have two answers there, because C I defined as the velocity of the 5 kilogram mass final. One of those is correct, one of them is not.
Can we define it right now?
Oh,
Or do we have to keep plugging it in?
No, we can figure out which one's valid and which one's not.
is it 3 because the first object had more momentum?
No.
Oh, it can't be 3 because it started with 3 and it has to lose.
This first solution is they haven't hit yet. All we've said, mathematically, we said momentum is the same and the kinetic energy is the same. Well, if I have two objects closing in on each other like this, their kinetic energy at this point is the same as the kinetic energy at this point, same at this point, and then they hit and bounce. So the solution of they never hit is not valid.
So it's -1.
So it's -1.
And then we can figure out D just by doing like some simple math.
D is 12.
D is
Or 6, I mean.
3.5 minus 2.5 C, so that is 6 meters per second. And if you plugged into the other one, 3.5 minus 7.5 is -4, which is the velocity of the 2 kilogram mass before the collision. The advantage of this technique is that I have immediate validation whether I've done it right or not, because one of the answers, the one that's not the actual final answer, but one of my solutions to the math is they haven't hit yet.
Will that always be the case?
Yes,
Okay.
but we want the other one.
Okay. Ooh. I like this. This isn't that.
And there are a number of people who prefer this technique because, you know, it's straightforward. I have conservation of momentum, I have conservation of kinetic energy. The tricky part, the